I am always very interested in anything new developments in science and technology, or even human behavioral understanding that can help with climate solutions. And this is a paper that is on nanotechnology solutions for the climate crisis. Well, crisis is a word that not everybody accepts, but let's just say for climate solutions. And obviously, I'm not an expert on nanotechnology, so I will just give you enough of a idea of what the paper is and what the applications are that are being proposed here. And you can follow up and read up more if you are interested, or ask experts for more details that I'm not going to provide in this brief introduction, right? Climate change is one of humankind's biggest challenges, leading to more frequent and intense climate extremes, including heat waves, wildfires, hurricanes, ocean acidification, and increased extinction rates. So this is people coming from nanotechnology side, and they are using standard jargon, including crisis. So you have to, if you're a climate scientist, you have to use your own subtleties about what do we mean by increased extinction rates, right? So this is complicated with baseline issues and so on, but obviously many species are suffering, so I'm not going to make light of that fact. Nanotechnology already plays an important role in decarbonizing critical processes. Still, despite the technical advances seen in the last decades, the International Energy Agency has identified many sectors that are not on track to achieve the global climate mitigation goals by 2030. What is the climate mitigation goal? You can think of that as the 2 degree C warming target and the 1.5 degree C warming target by 2100 with 67% probability. Here, which means we have to be at some level by 2030 in terms of the trajectories of reducing our emissions, deploying renewables, and phasing out fossil fuel and so on. Here, a multi-stakeholder group of nanoscientists from the public, private, and philanthropic sectors discuss 4 high-potential application spaces where nanotechnologies could accelerate progress. Batteries and energy storage makes sense. Catalysis for producing, let's say, hydrogen in a very cost-effective and without emissions, coatings, lubricants, membranes, and other interface technologies which allow harvesting of energy, water, and so on, and capture of greenhouse gases, carbon capture, utilization, and sequestration, maybe also capture other greenhouse gases. This comment highlights opportunities and current gaps for those working to minimize the climate crisis and provides a framework for the nanotechnology community to answer the call to action on this global issue. Right, so I'll just show 2 figures and we'll read the outlook they have. Nanotechnology for climate solutions, examples, so this is a better way to see it, nanotechnology for climate solutions. Examples of nanotechnology-enabled solutions for climate-intensive processes. Examples shown illustrate nanomaterials and technologies for batteries and energy storage, greenhouse capture, interfaces, and catalysts. So let's just look at those. MXene, maybe it's pronounced Maxine, is also a material, 2-dimensional, like graphene, but it's not exactly graphene, obviously. So with nanotechnology in the center, we obviously know what nanofibers are, quantum dots, follow up on that if you want, carbon nanotubes. Graphene is a material that has made a lot of noise, that applications are still not widespread. Metal oxides, metal organic frameworks are they are mixing metal with ligands or organic molecules which have special properties like filtering out things or even capturing humidity from the air to produce water and so on and so forth. And triple junction catalyst, catalysts for producing various things like hydrogen, as I mentioned. So being rather brief there, but read the paper. Batteries and energy storage, so grid storage, battery chemistry and architecture, and portable power. So here we have greenhouse gas capture, sorbent direct capture and mineralization. So sorbent is where you absorb it like a sponge and release it somewhere safely into a capture site, let's say. Direct capture is of course from the air. As air flows through, you precipitate out, and mineralization is also converting it into calcium carbonate or so. Okay, and here interfaces, so membranes, thermal interfaces, lubricants, could be for again removing pollution in water, in air, and thermal interfaces for efficiency of energy, appliances, everything else. And here you have catalysts, so sustainable energy, construction materials, and chemical production. So not much of a detail, but a few more details here. Greenhouse gas emissions reductions by sector and potential nanotechnologies to meet the 2030 targets. High emission sectors, industry, electricity, transportation, and buildings are high opportunity areas for nanotechnology enabled innovations to make a step change impact to meet global climate goals. More information on the 2022 global emissions and 2030 targets, please refer to reference 25. Okay, so basically we have estimates on how much carbon has to be removed from the system, because there is a linear relationship between warming and cumulative carbon, and we know how much we are emitting per year, so we can use that to back out an estimate of how much more carbon we can actually emit to stay on target by 2030, 2050, and 2100. So here are gigatons of CO2 with potential for industry. So this is about 2022 greenhouse gas emissions by sector and 2030 emissions targets by sector. So we have to reduce here, let's say we're going from about 9 to about 7, so a couple of gigatons here. Electricity, about 75% of the emissions come from electricity, but electricity is or power generation, but that's used in all other sectors like industry, transportation, buildings, agriculture, etc. Right? So nonetheless, generation of electricity is still a high emission industry. 2022, it's over 14 gigatons CO2 per year, so you need to more than halve it, so well, almost halve it. Transportation has a little room to go, or has to reduce by a little bit. Buildings also have to more than halve, right? So we are looking at catalysts, greenhouse gas capture, batteries, and interfaces here. Nanotechnology-enabled green hydrogen can serve as a precursor for many high-emitting chemical feedstocks, so that's for the industry. Also, nanoporous aluminum formate could be a cost-effective and highly selective point of source capture material, where emissions are being produced is the best place to capture them. So that's point of source capture, and that's $2 per kilogram, which is very cost effective, although life cycle analysis is always essential. Sorry about that. For electricity, alternative battery chemistries and nano architecture can match lithium-ion batteries at a lower cost. So lithium-ion is now the most popular, most dominant. There are issues with mining, recycling, and so on, but there is also need for other ideas. So sodium is picking up now, sodium-ion, for example, solid-state batteries, and so on. Calcium oxide nanocatalysts synthesized from waste materials improve biofuel production. So you can go and read the details there. So the 2022 total global emissions were 37 gigatons CO2, so that's obviously for that year. 2030 total global emission goals are at 24 gigatons CO2, so a 35% reduction to stay on target for the 2100 goals, or even net zero by 2050 and so on. In transportation, super lubricity has been achieved with various nanomaterials reducing friction to below 1%. Friction in moving parts and vehicles is a massive business. So if you can reduce it to below 1%, efficiency is going to go up tremendously. Nanocomposite silicon anodes increase the energy density of lithium-ion batteries. Okay, so that makes them more efficient. Buildings, direct air capture programs with nanotechnologies such as metal organic frameworks are contributing to capture contributing to the capture goal of 1.1 gigatons of CO2. So no matter what we do, there will be irreducible emissions. We haven't started reducing emissions yet, bending the curve, but it's pretty much clear that carbon capture is going to be part of the solution. So we must get good at it and meet the numbers like 1.1 gigaton of CO2 per year. Nanotechnology enabled electrochromic windows could save up to 40% energy demand for building heating and or cooling. So building energy demand is going to dominate by 2050, is expected to go up tremendously, and of course that also comes with steel and cement production and so on. Okay, so jumping ahead to outlook, reaching net zero emissions by 2050 as well as substantial near-term emissions reductions by 2030 are needed to avoid the worst impacts of climate change globally. There is a unique opportunity for nanotechnology to contribute to this goal, as we just saw with the schematic, by focusing on high emission sectors such as buildings, electricity, industry and transportation. Urgent action is needed to rapidly scale up and implement new climate solutions, drawing insights from successful nanotechnology applications. Okay, so nanotechnology is used broadly here, but if you include things like quantum dots or we're not talking about nanoparticles here, but nano is, reducing things to nano is also helping in medicine and so on. Globally, buildings account for almost 9.8 gigatons of CO2 released into the environment each year, out of around 40 or so that we are at, without accounting for non-CO2 greenhouse gases, which would put us above 40. So these are mainly from heating and cooling and must decrease to 4.4 gigatons CO2 per year to reach net zero globally by 2030. That is, chromic nano coatings, for example, thermochromic, electrochromic and photochromic, can change a window's optical properties based on external stimuli and thereby decrease solar thermal impact and hence the need for cooling. Electrochromic windows alone have the potential to save up to 40% of energy demand for building, heating and or cooling. Awesome, right? Decarbonization of the electricity, and these are easy retrofits. You don't need to replace windows, you just need to coat or replace the glasses with coated glasses. And then you can do you can do calculations to see how long it will take to recover the cost of doing retrofitting, right? Decarbonization of the electricity sector will heavily depend on advances in batteries and energy storage to tie intermittent renewable energy to the grid. According to the IEA, the electricity sector will need to abate 7 gigatons of CO2 per year globally by 2030. Nanotechnologies are already helping achieve higher energy and power densities in traditional lithium-ion batteries, and new approaches are being added to the market. Nanotechnology-enabled iron-air batteries for grid storage are currently under commercial development, with claims that they can achieve 100 hours of storage at 1/10 the cost of the traditional lithium-ion batteries. So safe mining of lithium and eventually also having alternatives is important, but if you can do them at much lower cost, that's much better. Improved nano architecture could also allow for other emerging battery chemistries with optimized characteristics to match lithium-ion batteries at a lower cost, but access to advanced processing and manufacturing techniques currently represent a bottleneck to accelerate the scaling up of these solutions. Researchers and entrepreneurs in the United States have voiced the need for a Manufacturing USA Institute focused on advanced battery manufacturing to help reduce cost and risk of new materials and manufacturing techniques. There's also the idea of removing dependencies. If China controls all the critical minerals and materials, then all your plans for climate action, economic growth, sustainable growth, etc., will depend on China. So having alternate materials, new materials, manufacturing techniques becomes important for independence, energy security and so on. Industrial sector made up of aluminum, cement, chemicals, Light industries such as food processing, textiles, and consumer goods, paper, and steel needs to reduce emissions by 2 gigatons of CO2 per year globally by 2030. Here, nanocatalysts have an enormous role to play. A promising approach is the development of green hydrogen, but the process is currently 2 or 3 times more expensive than producing hydrogen from a natural gas. This is how engineering typically works. You show feasibility first, then you keep pushing the technology readiness levels to as high as possible to make them economically viable and competitive against other approaches like producing hydrogen from natural gas. Cheap and abundant green hydrogen can serve as a precursor for many high-emitting chemical feedstocks such as ammonia, methanol, ethylene, propylene, benzene, toluene, and xylenes, which account for around 75% of the greenhouse gas emissions in the chemical industry globally. So green hydrogen, of course, is where you're catalyzing something like water and producing hydrogen using renewable energy, no emissions. Several companies are working on novel ways to produce and utilize green hydrogen. For example, a company developed heterogeneous nanocatalysts to produce green hydrogen. There is the Air company reference, that link. That is, this green hydrogen is then used to transport captured CO2 from industrial plants into value-added chemicals using a nanocatalyst. So you are doing carbon capture and utilization with the help of nanotechnology. Optimized electrolyzers, earth-abundant nanocatalysts, and improving nanocatalysts' lifetime and reliability could decrease cost and scale up circular economy solutions. To date, there are 40 greenhouse gas capture and utilization commercial facilities accounting for a modest 0.05 gigaton CO2, which is tiny, captured annually worldwide. But again, you will be trying forever to scale it up till we accomplish something that is practical. Increased commercial and government support has propelled over 500 new pilot plants, demonstration projects, and commercial plants in various stages of development. Think of the Wright brothers and one little hop they took, which now allows us to go out to space, out of the solar system, Mars, Moon, and so on and so forth. The transportation sector currently emits nearly 8 gigatons CO2 per year globally. By 2030, a reduction of almost 2 gigatons CO2 per year is targeted through enhanced efficiency and technology adoption. Multi-wall carbon nanotube additives and carbon coatings on silicon particles in lithium-ion battery electrodes are already being used in commercial electric vehicle batteries. One company whose batteries are being deployed by a major automobile company claims that its nanocomposite silicon anode lithium-ion batteries can currently achieve 20% more energy density than traditional lithium-ion batteries. So you have life cycle of the batteries, how many times you can recharge them, and energy density is another critical parameters in addition to cost, of course, right? So this also diminishes the use of critical materials by doing this nano coating of the silicon anode, nanocomposite silicon anode. Nanotechnology could also hold the key for mobile energy delivery beyond batteries, including hydrogen storage and fuel cell solutions. Across a variety of critical technology sectors, nanoengineering can enable the kind of performance leaps needed to mitigate climate change. However, the severity and urgency of the issue demands that we consider not just technical potential but also the economic, manufacturing, workforce, and adoption hurdles that could impede the realization of nanotechnology's potential before irreversible harm is done. Well, basically, we need to, phase out the investment in fossil fuel dependent technologies like producing internal combustion engines, let's say, and bring in new manufacturing processes and train the workforce and worry about technical transitions to use nanotechnology's full potential. Given the urgency, it's important to prioritize drop-in technologies that can be incorporated into existing infrastructure and supply chains, and to use earth abundant materials to remove barriers for adoption. There are many federal resources available and so on, so I will jump ahead. Public private facilities are there, they can produce, so they can provide advanced manufacturing capabilities. Artificial intelligence tools are being developed to help move low technology readiness innovations towards commercial deployments. So technological readiness level has to move up quite rapidly. Nanotechnology enables step changes in semiconductors, powering the AI revolution, which can help accelerate climate change solutions by rapidly marrying capabilities with technical demands. AI-enabled nanomaterials design may eventually enable long sought after technologies such as high temperature superconductors, a virtuous cycle enabling yet another step change in computational energy efficiency. AI is a very intense computational big data problem with huge energy demands. So any computational energy efficiency is going to be helpful, as we talked about in another podcast before this. Nanomaterials, size, dependent properties, and the ability to tailor materials to desired physicochemical properties can drive and already are driving technical solutions in the realms of energy storage, catalysis, interfaces, and GHG capture. These are environmentally and economically valuable opportunities, many of which have shown real climate impact and economic viability. For its part, Nano4Earth is mobilizing the entire nanotechnology community, researchers, entrepreneurs, government, industry, investors, and philanthropists to combat climate change on all fronts. So you can go and look up Nano4Earth. It's Nano4Earth, but it's Nano4Earth as an abbreviation. So I thought this is really interesting enough that I should report on it, even though I am not a nanotechnology expert. But I hope this introduction helps you or helps you enough to pursue further details if this is of interest for you. Okay, so we'll meet in the next topic. I'm always afraid to say what it is because I will tend to change my mind. We'll look at Project Drawdown and where it's having some successes, which is a really, really interesting and important and very critical project, Drawdown. Okay, I have a full course series of podcasts on Project Drawdown as well, and this will go in the new findings in that section as well. Okay.